I've prepared some slides for today to introduce our research and profile, and I hope also to inspire a bit on what our perspective is on the psychology of user-energy interaction and how we could support humans in their resource regulation when it comes to resource-efficient mobility, be it time or else. That was my introductory slide, and to give you a bit of context in the beginning. So let's introduce a bit like the ecosystem where my research or our research is happening, because as you may know, Lübeck is not just the queen of the Hanseatic League, but it's also quite a nice place to do sustainable mobility research. Not just, you probably know these pictures of Lübeck or may have some associations like this. Sweets and nice city, medieval city. But of course, there's also, as it is in the north of Germany, a lot of green electricity available for electrification. We also had one of the first intelligent range management systems in electric buses in public transport in a field trial setting here in Germany. And we had the first ride-sharing service in Germany that was operated or is still operated by a local bus company, so not a private company, but by the community, so to say, or by the normal bus company or bus operator. And we have car sharing in Lübeck since 30 years now, and also a very big, so when it comes to the share, very big electric fleet, and the first fleet that also has bidirectional charging in a living lab setting implemented in car sharing. So I think it's quite nice, the ecosystem in which we can work. And our university is situated in the south of Lübeck, in the university district, where there are also several startups, and so it's quite a nice ecosystem to do research. And my professorship in specific is located at the Institute for Multimedia and Interactive Systems. So we do research on interactive technologies in many fields of applications. So we have like creativity lab, design thinking lab, usability lab, driving simulator, mixed reality lab, and so on. And we draw a lot from our bachelor and master degree program in media informatics, so where we combine this computer science, psychology and design expertise. So here's just a glimpse into this study program from our media informatics EMI award. Okay, and as a short introduction to my person, so I'm just a psychologist. Okay, yeah, so I'm just a psychologist, but now I'm a professor at a computer science lab. And I've worked in electric mobility since 2008, since these first mini field trials with BMW and other partners here in Germany in 2008 and the following years. And so since 2017, I finally built up our group here. And so our group is mainly, is quite diverse, to say. So we somehow integrate media informatics, design and psychology, but with one specific application area or core topic, which is sustainable digital resource regulation. And we do this basically on the following research lines. So basically we say that we as humans must bring two different types of resources into balance. So on the one hand side, our internal resources, so psychological and physical resources, and on the other hand side, external resources we use to satisfy key needs, such as, for example, mobility. And we go specifically into these contexts, real life contexts, to understand resource regulation better. So quite a lot of contexts like e-car sharing, CO2 tracking, or energy efficiency at sea. Or also human energy and fitness tracking on the other part. And we developed quite some methods. So, for example, our driving simulator, e-car simulator, or our scales to assess affinity for technology. And in each and every context, we ask the same two questions, which is first, what are the key challenges for human resource regulation in this specific environment? And second, how can humans be optimally supported in the regulation of resources via system design? And if you want to know more about our research, of course, you can have a look at our Google Scholar profile, or at my Google Scholar profile, or you can also just have a look on our YouTube channel. Unfortunately, there's lots of material in German, but there are also English videos around. And you will see that if you understand German to some degree, that it's always about the same formula, which is sustainability is product or equals human and technology. So, for example, you can have a look on our research on energy interfaces or on eco-shipping or on the topic of range management in electric buses and ride sharing. Okay, so far for the general introduction, let's start. So I guess that we have all heard of range anxiety, and I also think that maybe some have heard of range stress. So this was actually the first paper where we tried to, so in my dissertation still, we tried to describe and explain and predict range anxiety from the standpoint of a psychological theory, which is the transactional stress model of Lazos and Folkman. And also, as you see here, we use, and we still favor this approach, use control theoretic approaches to better understand the interaction between humans and machines. And maybe you may also have heard about psychological range levels. So still, typically in the industry, we optimize technical range. Yet in the end, from our perspective, it would be beneficial if we would rather conceptualize range in electric vehicles based on these three levels of comfortable, performant, and competent range. So maximize the psychological range. So this would be the way to change the psychological range experience in a beneficial way, also in mobility and professional mobility settings. And of course, then there's the topic of range preferences, where in these mini field trials we had the first chance to really examine how practical experience changes drivers' range preferences. And of course, then there's a big topic of charging. What can we learn from how do people charge other batteries, like in mobile phones, and how we can transfer it to a control theoretic model of user interaction with charging and with battery resources in terms of charging behavior, and how can we, for example, use this knowledge and this theoretic approach to better design vehicle-to-grid, so smart charging concepts. So I could tell you of all these topics today based on these field trials that I mentioned, but I would like to start at another point by asking what is energy efficiency and why is energy efficiency so difficult for us as humans? I would say the key question in the end is how do we humans deal with precious resources? Because we are doing it every second of our life, right? We breathe, we move and utilize the power of our muscles to do so. We invest time to gain knowledge. We wait for something like the train and use the time to check new messages. So every second of our life is resource regulation. And no matter whether it is time, money, chocolate, or electricity, the same psychological principles apply to all kinds of resources, which is we prefer winning over losing, but we are not completely rational in this. So that's what basically psychological behavioral economics shows us. So for example, prospect theory. So losses hurt us twice as much as gains make us feel good or give us pleasure. And there's more. So that's the first effect. So behavioral economics can help us to structure and understand human resource regulation. But I mean, one question that is still not clear from the prospect theory is, or so far not clear, is what actually is a gain. Prospect theory says we judge gains and losses in relation to our subjective reference value. For example, if your battery forecast on your mobile phone says you have 2 hours of battery life left, and 2 hours later you look again at your phone and it still says that there are 30 minutes left, then probably you feel that this is a gain. So in the end, this is what we call framing in behavioral economics. So the framing of resource dynamics and inherent resource transactions. And the more information about resources reach us via HMIs, the more relevant this topic becomes. So I would conclude so far that representations of resource dynamics can influence our perception and behavior through framing. For example, in this vehicle, imagine you're driving your hybrid car, and for every 50 watt hours of energy that you recover through regenerative braking, you get a green car as a gift, like here. So in the end, does this make you feel it's like a loss or a gain? And what would be your behavioral strategy you develop when you want to optimize energy efficiency based on this consumption interface? So what I want to express here is that in the end, users can develop false mental models. For example, it is good to use regenerative braking as often as possible due to suboptimal energy interfaces. So the question is, how can we improve this? And we thought, let's just teach users the golden rules of eco-driving. And then we collected rules from driving manuals, and we collected a lot of eco-driving knowledge. And in the end, we came up with an experimental design where we said, let's compare what car manufacturers typically give as eco-driving tips, and what, as the red part here on the slide, what psychology would say how you should present eco-driving tips. And we tried out two different variants. First, clear if-then rules, so know why. And second, these if-then rules, and in addition, mental model information. So an explanation why these rules are energy efficient. So know how and know why. And what we found here is, so we just gave people a piece of paper with a set of 15 golden eco-driving rules in different kinds of formulations, and then they drove for 1 month, and then we logged their fuel consumption for the month before and in this month, and we found that in the end the basic formulation and the if-then rules don't contribute to fuel efficiency at all. Only if we add the know why component does it result in some significant effect. But of course, we all know no one reads instruction manuals. So the question is, of course, how can we integrate such golden rules, such energy efficiency rules, into a system, in a training system, so like in such an app. So that's one bachelor thesis from our media informatics students, and there's also video, unfortunately in German, on our YouTube channel that explains a bit more on this. So long story short, I would say we need to think how we represent energy efficiency, and in the end we need action-integrated energy interfaces. And as you will see in a moment, this boils down in the end to optimize efficiency metrics and indicators. So what can we as automotive interface researchers do for sustainable mobility? I would say we can do quite something, because we can guide users towards energy efficient driving, like I showed you, and we can increase awareness and understanding of energy efficiency, and we can in the end support energy efficient decision making in a sense of or in the understanding that energy efficiency is always the product of technical potential and user. So in the end, I would say to realize the energy efficiency potential, we need the user perspective strongly. So the question is, how can we design effective energy interfaces, and how can we make eco-driving as easy as possible? So how can we integrate the knowledge from engineering, so control engineering mostly, and psychology to answer the question, what is actually energy efficient, and how should we best condense the rich energy flow data to integrate well with human information processing? So to design in the end effective energy interfaces. And I think it's really important to design these metrics, user-centered efficiency metrics and indicators, because in the end, our energy interface design is about aggregation and representation of energy data. And so far, there's still surprisingly little research that focuses specifically on this topic. Okay, so what is actually energy efficient? So this would be one answer. but because we can break this down a bit in a more specific scenario. For example, if I ask myself, okay, let's say I want to drive to my favorite beach at the Baltic Sea near Lübeck. So what is the most efficient way to drive the 40 kilometers to the beach with my car? I would say the most efficient way is to take the bicycle. Okay, and let's say I have to take the car, then the most efficient way is, of course, to drive this 30-kilometer route to the beach. And here it's interesting to see that our most common energy efficiency metric is energy per distance. So, for example, kilowatt hours per 100 kilometer. And this has a core blind spot because it gives us no incentive for taking a shorter route. So, in the end, we need metrics that correct this bias and make users aware of this blind spot, I would say, as a first design idea or notion. Okay, and let's say we took the shortest route, then what's the most efficient way to drive the 30 kilometers to the beach? So if you drive with constant speed on a flat road, then of course it's rolling resistance and aerodynamic resistance, and while rolling system is constant and dependent on the road surface, aerodynamic resistance is something that is really relevant for us because it increases contractility with speed. So the cost of driving 10 kilometers faster increases the speed, as we know. And so in the end, we need interface indicators that help users trade energy consumption versus travel time, right? So that help users to trade time efficiency for losses in energy efficiency. Yet there's one further important factor, of course. Electric motors are most efficient at moderate speeds for a typical battery electric vehicle and at moderate acceleration intensities. That's basically what efficiency maps show us. So for example, at this vehicle speed of 60 kilometers, a pedal position of 40% would result in high energy conversion efficiency. But unfortunately, life is more complex than choosing just one as the optimal speed. In reality, drivers execute a large number of acceleration and deceleration maneuvers, and this here is just a short driving segment. So drivers continuously have to make decisions that impact energy efficiency. So how do humans control their behavior in such an environment? I would say that in everyday driving, drivers typically balance different driving goals. So I would say, in the end, we want to get there alive, in time, stress-free, with reasonably energy costs and without disturbing other traffic. And drivers continuously adapt their behavior to balance these goals. And such dynamic aspects of behavior can be and have been modeled particularly well with control theoretic frameworks, yet so far mostly with a focus on safety-related aspects of driving. And we have made a very first shot, to also do this for the topic of energy-related driving behavior. And I don't want to go into this model. I only want to point to one box, which is the subjective expected utility of strategies. Because what do safety, time, energy, and pleasure all have in common? I would say they are all resources, and all resources are subject to the same psychological principle, which is we try to achieve gains and avoid losses, as we have already seen from behavioral economics. So our decisions are driven by bounded rationality. So we are not completely rational in this achieving gains and avoiding losses. But basically, we can use this as a good model for the start. So we can say that in the end, the control of energy flows is the economic transaction of an input resource, for example, electrical energy, for an output resource, in the end distance driven, or ultimately or directly or more nearly, for example, kinetic energy. And now the key question, as we have seen before, is we can frame these resource transactions in a specific way. And any energy interface design, if we want it or not, constitutes such a framing. So we have to be at least aware which framings our energy interfaces establish. For example, an acceleration. So nowadays, drivers typically have one salient information source, I would say, to perceive the energy efficiency of the current acceleration, which is the instantaneous consumption indicator, which is based on this energy per distance metric. And research shows, or very new research shows, that drivers have quite some difficulties deriving the actual fuel efficiency of accelerations from this indicator, because of course they do not compute the integral in their head. They rather orient to the peak height. So the peak height, there's kind of a peak bias here. So the question is, in the end, how can we accurately represent energy consumption? And I would say that from what I presented before, there's one promising approach to de-bias perception, which is, for example, if we use instantaneous consumption traces that help us to more visually grasp this integral instead of the peak and the duration of an acceleration. But of course, there needs to be more. If we think not just about the indicator, but about the metric for efficiency when it comes to acceleration. And I would say that energy per metric distance is not the most accurate here, but in the end, the transaction that is happening is investing electric energy to establish kinetic energy. So it's the conversion efficiency of the electric motor that is especially important here. And if we take this conversion efficiency metric and say, okay, let's compute the instantaneous conversion efficiency indicator, then it would be a bit like if we see this as a cake viewed from the top or above, and if we would then just slide one thing out, one piece of cake out, and then you would have something like an efficiency terrain profile as seen here. And we've tried this, or we have established over the last years a test environment to examine such interfaces such as this, both in our driving simulator, but also in our real world real car vehicle. And here you can see, and I hope that this somehow translates via the web conference, how this would look like in real life. And if you can see it now, then you will see that it's, of course, quite distracting. It will be quite distracting. But I mean, this is just a start, right? So now we would, in the next step, have to optimize this for workload. And there are a lot of possibilities to optimize it. Okay, to conclude this chapter and to come to to my final topics that I will just want to show briefly to you. There's one problem. If you just visualize to people this conversion efficiency metric, then there would be a problem because there's a blind spot, because it doesn't penalize unnecessarily accelerations, this metric. So in the end, it would be important to have at least 1 second indicator, which is an indicator that indicates when too much kinetic energy has been built up compared to what can be efficiently utilized. So without mechanical brake, and ideally also without regenerative braking, or at least when you need regenerative braking, then in an efficient way, maximum efficient way. So this could be one solution you can see here on the down right side, how this could look like. Okay, so what I would say, what are the takeaways here for this section? I think we really have to reconsider how we represent energy efficiency in vehicles, and how we align these representations better with human information processing, behavior economics, and the actual energy efficiency of driving behaviors. So we need to find the optimal aggregation of energy flow time series data. But of course, this is only one step in a larger area, because I mean, how do we integrate this with automated driving functions? This is still, I would say, quite a complex topic, as far as we realize that drivers are quite sensitive to automatic energy optimization when it comes to, does this meet my driving style preferences? Or is this transparent and understandable why the vehicle drives in this way and seemingly thinks that this is an energy efficient way of driving? So there can be a lot of counterintuitive driving styles by an automated vehicle. So the driver needs to be, from our perspective, somehow in the loop. And of course, there are further questions like, how can we make electric energy more tangible? or how can we also address user diversity in variables such as affinity for technology interaction. So these are some of the questions we want to examine in the next years in our driving simulator. And there's also a paper on this topic that you can download when I share the PDF afterwards. So I can only repeat that we need action-integrated energy interfaces, which means efficiency metrics and indicators. And to finish the talk, I just want to go into three more or less small other topics. First of all, think of the situation where you have bought a rather expensive battery with 4 wheels in the form of an electric bus. Now the quite exciting question for a bus company is how can we get this battery on the road in the best possible way? And first of all, the question is, what is optimal? And I would say optimal is maximum resource efficient. So what is resource efficiency here? I would say that the maximum resource efficiency of electric buses is how much daily mileage can you achieve with how much battery capacity. And this in the end boils down to the question, how can we achieve the maximum daily mileage with electric buses? And this was essentially the core question of our e-bus project NUR-E between 2018 and 2020, where we tried to develop different approaches to reduce uncertainties, increase comfortable range, and in the end optimize range management in a real-life setting. Basically, we worked on 2 pillars of range management. First, assistance for range assessment or range estimation, and second, assistance for range extension or optimization. So like filling this gap between what is usually displayed and what could be displayed on the range display if conditions would be optimized. Like for example, eco-driver training would be used. Yeah, and we worked there both on an analytical part with data science and psychological study approaches, and on the other hand side also on interfaces such as this or this. And of course, I'm not being serious that this should be ever implemented in an electric bus, but it's more an idea to playful exploration of design opportunities or to somehow span up the possibility space of designs. And I think that these student works that I showcase here show give quite a nice inspiration for design possibilities. And for this project, there's also an ebook on implementing range management in electric buses. Unfortunately, you have to be able to read German to utilize this ebook. So, range management, I would say, can support the efficient utilization of battery resources. This brings me to my second last topic that I only want to mention quickly, which is that, of course, intelligent resource management in mobility is not just about one battery, one driver, or car, but it's about sharing. How many people can we make happy with just one vehicle? So vehicle pooling, car sharing, ride pooling, and ride sharing. And this is what we examined, for example, in our eCar Share project that I can talk about a lot, but I will not do it now, but just show some pictures. And what we also did in our ride-sharing project together with the local bus operator, Stadtverkehr Lübeck, where we examined and are still examining how we can best meet individual mobility demands and design a ride pooling service that is really resource efficient and that gives people autonomy, develops their mobility competence, and so on. This brings me to my very last topic. After I read out the thesis, which is that in the end, I would say that intelligent mobility resource management can support the efficient utilization of mobility resources. And this last topic is the topic of charging, which is Remobil, so bidirectional charging. So I only want to mention it quickly that we have a lab at the university here where we can study interesting user-related research questions of optimized bidirectional charging. I just go quickly over this. So there's a lab which is situated on our university campus, and there are quite some people or different stakeholders who take part in this lab and who use these vehicles. And this is the last slide that I want to show you. It's the basic system architecture of the Renewable Lab, which constitutes of, on the one hand side, hardware, so the cars, and separate battery storage and the bidirectional chargers. Then a lot of infrastructure for measuring everything that is possible, and of course an infrastructure to collect subjective user data. And then the plan is here with this infrastructure to test several of these VxK enablers. So this could be incentive schemes, information systems, or at one point in the future, maybe something that tells me, okay, Thomas, based on the data from the last 3 months, you will need maximum range of 100 kilometers tomorrow morning at 8 a.m. If you are fine, I now activate the smart charging, and this will save you and us something, give you more green electricity, and will not limit your flexibility. Okay, thanks for your attention.